So transition metals are a special group of metals, and they are the block between group 2 and group 3. Now, that's actually untrue, because there's a difference between transition metals and D block elements. So, D block elements are elements that have an electron in the D suborbital. So that would be exactly what I said between group 2 and group 3. There is a block, and they are all D block elements. Transition metals have at least one ion where the d orbital is only partially full. Now, this is very, very important, because this explains that D block and transition metals are similar, but there are some D block elements which are not transition metals. In fact, scandium and zinc are not transition metals, and we're going to write the electronic configuration on the board. But anything else is a transition metal. Okay? So, let's write the electronic configuration from scandium to zinc. And in the meantime, whilst I'm writing this, you might want to try it for yourselves. So, scandium is 21 and zinc is 30. So there's scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. So scandium is Ar 3D1 4s2, titanium is Ar 3D2 4s2, vanadium is Ar 3D3 4s2, chromium is Ar 3D5 4s1, manganese is Ar 3D5 4s2, iron is Ar 3D6 4s1, cobalt is Ar 3D7 4s2, nickel is Ar 3D8 4s2, copper is Ar 3D10 4s1, and zinc is Ar 3D10 4s2. Now, there are two exceptions there. The exceptions are chromium and copper. Okay, so chromium and copper are exceptions. Why? Because one of the 4s electrons has actually gone and filled the d orbital. In copper to make it half full, and then zinc to make it full shell. Now, I don't have any scandium salts, but I do believe that I have a zinc salt, zinc chloride. And in fact, zinc chloride is colorless or white. Okay, white and colorless are the same thing for us in chemistry. So this is zinc chloride. Now, What about their ions? Transition metals normally have variable oxidation states. Today, I only want to speak about Sc3+, where it will be that of argon. Okay? Zn2+, where it will be argon 3d10. And let's, for example, do Fe3+, where it will be argon and 3d5. Here, you might realize that scandium has an empty d orbital. So the d orbital is not partially full. Zinc has a full d orbital. So again, it's not partially full, it's completely full. And iron has a partially full 3d orbital, but it only has 5 electrons. It's half full, but it's still not completely full. Now, this is important because there are characteristics for transition metals that we're going to be discussing soon, today in fact, where we have the transitions in the d orbital. So 3d10 is stable. So zinc cannot lose any more electrons. Argon, the configuration of argon is completely stable, it's a full octet. So again, we will not have any more loss of electrons, and therefore scandium 3+ is very stable.
Sir.
Now, 1 second. Kyra, zinc and scandium are d block elements, but they are not transition metals. Zinc and scandium are d block elements, but they are not transition metals. Yes, Bondi?
Xej saqsita Kajra.
Okay. No, I'm reading the comments. I'm not answering Kyra asking this. I'm reading the comments and I'll include them in the lesson. Okay? Now.
Sir, tkun tista' tikteb taż-ZN iktar il fuq, please, għax mhux qed jidher.
Okay. 1 second. Okay, you should be able to see it from what I've got. But Zn is argon 3d10 4s2. Zn2+, you lose the outermost electrons. And the outermost electrons would be 3d10. I'm using the argon electronic configuration as shorthand. Argon, let's write it here. Argon electronic configuration of argon is equal to 1s2, 2s2, 2p6, 3s2, 3p6. So instead of writing all that every time, we're writing the shorthand version, and the shorthand version is writing argon instead of 1s2, 2s2, 2p6, 3s2, 3p6. This is something going back to our first chapter, okay, where I will not use the green, okay? Okay? I will not use the green. Because we don't like it. Even though I'm from Army and for our Festa, I'm covered in green normally, or I used to, when I was your age, a few years back. Now, chromium and copper are exceptions. So, chromium and copper are exceptions. Thermodynamically speaking, so when we're speaking about the energy levels, okay, again, I'm going to re-explain, but this is something we've done in the first chapter. But thermodynamically speaking, chromium and copper have a more stable conformation when the d orbital is either half full or full. Therefore, they will excite an electron from the 4s2 orbital, from the 4s orbital, and half fill their orbital to either have a half full d orbital or a full d orbital. It's just more energetically stable.
Sir,
Yes?
could you re-explain why they aren't transition metals?
Yes. So, give me a second. Gabriel, you can ask whenever you want. And Emma, I don't want to say that only scandium and zinc are not transition metals, because yttrium is also not a transition metal, cadmium, mercury, and copernicium. These are all non-transition metals, okay? From period 3, it's true that they are the only ones. So
Okay.
a transition metal has an ion that is only partially filled d orbital, okay? So partially filled d orbital means that the d orbital is neither 0 nor 10. For example, let's write for copper. Copper can be either Cu plus or Cu2 plus. Cu plus is argon 3d 10, Cu2 plus is Ar 3d 9. Cu plus, in fact, is white. It's not a transition metal, or it's not a transition compound. But copper has Cu2 plus, which is actually a partially filled d orbital. So Cu2 plus is actually a transition metal. And in fact, Cu2 plus is a blue compound. If I can find my copper sulfate, I can show you. In fact, Cu2 plus is a blue compound. Okay? Taya? Okay, Kyle.
So the copper and chromium aren't transition metals
No,
because
Copper and chromium are transition metals. It's only zinc and scandium that are not.
allora copper and chromium x'inhu ma sir?
Copper and chromium have the exception how to write the electronic configuration. So look, normally we fill 3D1, 3D2, 3D3. So this should have been 3D4, right? Chromium should have been 3D4. But because you've got a half stable conformation which is more energetically favorable, chromium takes one electron from the 4s orbital and adds it to the 3d orbital. So you have to have two half-filled orbitals.
Dimma ġa konna minni għet l-chromium u l-copper għax qiegħda
Ija
fil-booklet.
diġà minnija fil-bidu le.
Hija kard.
It's fine, it's not a problem. You can ask whatever you want. But these are the type of questions that I explained earlier on, where send them to me, and once a day I'm going to upload a video that will actually explain a small part of a chapter. Okay? Cu plus is not a transition metal. Scandium, Claire, it's not a transition metal because it has 0 electrons in the 3d orbital in its ion. Remember, we are not speaking about the element, we are speaking about its ions. And for scandium, the ion is 0 electrons. There is an empty d orbital. Okay? Now,
Okay.
Ġifiri, zinc u scandium ma jiġux bħala transition elements għax jiġi empty d orbital jew xi ħaġa hekk.
wieħed empty u l-ieħor full. As elements, we don't consider as transition metals as the element, it's their compounds here. Okay? But as the elements, They are metals. They are just metals. Okay, so if I show you zinc, where is zinc? This chromium. Zinc, okay, it's just a dull black powder together with the powder form. So it's not a transition, it's not white, as you'd expect from transition from non-transition metal compounds. It's just black because it's a metal. Chromium compounds, dichromic, for example, is bright orange. Okay, so it's all about the ions. Up till now, are you okay with what a transition element is and what a D block element is? Do you know the difference between D block and transition now? You can type in chat if you want.
Sir, ġifiri scandium. Scandium atom huwa transition element, imma lion le.
Yeah. Scandium is D block. Remember, we're speaking about the ions here. Is the ion transition, yes or not? Okay?
Għalfej fuq lion imma mhux fuq l-atom.
Because the atom is not a compound, it's a metal. The atom, the metal, is similar to copper, zinc. They are all metals. But the properties of transition metals, when we speak about the properties of transition metals, it's the properties of their compounds. Even when you're going to speak about group 1 and group 2, you don't really speak about sodium, you speak about Na+, Mg2+. Because we're speaking about group 1 and group 2. Remember back to what you did at O level. Even here, the properties that you give, transition metals have colored compounds. It's the compounds that you are assessing. Yes, you're right, Jade. One second.
Sir,
Yes.
ġifiri CU plus
Yes.
huwa mhux transition metal.
Copper. It's a copper ħanamlu ħalih. Okay, we're gonna do chromium, manganese, iron, and copper on their own. So we're gonna speak about transition metals in general. And then we're gonna do those 4 elements on their own. Okay? Copper, you have 2 ions. You have Cu plus and CO2 plus. Okay? Now, Cu plus has compounds which are white. Cu plus is a non-transition metal. Okay? But CO2 plus is. So we say that copper is a transition metal because it has one ion. It has one ion that has a partially filled d orbital. Yes, all of these between scandium and zinc are all d block elements because the last electron for the metal falls in the d orbital. But transition metals needs to have the ion that is in a partially filled d orbital. They need at least one ion which is in a partially filled d orbital.
See.
Now, with regards to chromium and copper, I'll explain in a different video. Okay? I'll explain it in a video on its own so that you can listen to it a number of times, as many times as you want. I will not go into the physical chemistry aspect of it, which is, in my opinion, a master's level subject. Okay? It's just having a half full orbital. Or a full orbital, it's more stable. That's all you need to know. Scandium doesn't exist, Yannick. Because scandium doesn't exist. Scandium is 3+, always 3+. Now, who said say?
Jien sej. Allura li jiġu transition metals għax qed nitħawat, jiġifieri scandium u zinc huma non-transition.
L-oħrajn kollha huma
L-oħrajn kollha all right, okay.
Okay?
Thank you.
Now, so let me repeat what I written in the beginning. The block elements have an electron in the d orbital, so their last electron is in the d orbital. Okay? And transition metals need to have at least one ion, which has a partially filled d orbital. Issa, the next two things that I'm going to mention, and today I will stop as soon as I explain these two materials, these two things, will be oxidation number and size. We have around an hour and a half today, Gabriel. Don't worry, we're not gonna just say oxidation number and size and that's it. So, Emily, all transition metals are D-block, but not all D-block are transition. This is like all females are humans, but not all humans are females. Now, size. Size in chemistry matters, okay? And for transition metals, size remains more or less constant along a period. So normally we used to say that along the period, size decreases. But if you go from scandium to zinc, okay, size remains more or less equivalent. And by size, we mean the radius. So, size is more or less constant. The reason for this is that between scandium and zinc, electrons are added to the third shell. So, what influences the size? What influences the size in a compound? Is the distance of the last shell from the nucleus, not blue? That is the distance from the last shell to the nucleus. Now, if the last shell is the 4s2 electron, we are going to have to consider the 4s or the fourth shell as the size of the transition metals. So normally, for period 1 and period 2, we say that as the proton number increases, the shielding remains the same, therefore the pull on the outermost electrons is bigger. Because there was some confusion in the exam about this, are we all clear about this? The proton in period 2, okay, when you go to the right of the period, when the proton number increases, shielding remains the same, and therefore the pull on the outermost electrons increase, and therefore they are smaller. Not blue, yellow.
down the group. It
Lower.
gets bigger now.
One second. Down a group, they get bigger. But we're speaking along the period.
Because the period smaller. Exactly. Okay, thank you.
Now, here, the electrons are added to the third shell. So, along the transition metals, protons increase, but shielding increases as well. Why does shielding increases? Shielding increases because when you actually add the extra electron, you are not adding it in the outermost shell. You are simply adding it to the third shell, to the 3D shell. And therefore, this will shield the nucleus from the 4s shell, from the fourth shell, meaning that along the transition metals, shielding increases with an increase in the atomic number. Are we clear about this?
Sì, ġifiri, transition metals, it-tiri ta' shielding ma tapplikax għalihom bħalma kif fl-oħrajn.
Mhux ma tapplikax għalihom. This is why it's very important that you understand the theory, because the theory still holds, the theory is still the same, okay? So the theory states that shielding is going to neutralize the effect of the nuclear pull, okay? And therefore you're going to have an effective nuclear charge on the outermost electrons. That is the theory of shielding. Now, here, instead of adding the electron to the outermost shell, and therefore the shielding remains the same, you are adding it to the third shell, meaning that both the number of protons, so the nuclear pull, and the amount of shielding, both are increasing. And they are increasing by the same number, more or less, okay? It's one electron and one proton. And therefore, the effective nuclear pull, the pull on the outermost electrons, will be the same. Not blue? But these are trends, not the cursive period, just the cursive period, Xenia. These are the trends across the transition metals. So we can't say that this is true for all periods. The trend we're speaking about now is just true for transition metals. Oh, sorry, Xenia. Kaira. Okay? Now, ask. I expect a lot more questions on this topic. Now, yes, when you speak about chromium and manganese and copper and zinc, of course, there's going to be an increase in shielding, which means that both copper and chromium decrease in size. Okay, let me try and actually find transition metal sizes. Mela. So let me share the screen. So can you see that the size between scandium and zinc, they are mostly the same? Yes, from scandium to titanium and titanium to vanadium, there's a small decrease in size. But look at the massive decrease between potassium and calcium, calcium and scandium. These are more or less constants. Okay, and this is the reason why. I don't want to put you in a position where you get confused here because of this picture though. The theory behind it, now the theory, you can explore it a bit more. For now, just understand that the size is more or less constant. And it's similar to both period 5 and period 6. Okay? The sizes of these transition metals is more or less constant. Protons increase. Kyra. So this is the reason here. The protons increase. And when the protons increase, there is an extra electron. So going from iron to cobalt, iron has 26 protons, 26 electrons, and cobalt has 27 protons, 27 electrons. So when you go go from iron to cobalt, you've added one proton and one electron. The electron is not going in the outermost shell, it's only going to the 3D shell. So it's going to the third shell, which means that the outermost electron, the 4s suborbital, is going to have and is going to experience an increase in shielding. Okay? But this increase in shielding is going to be counteracted by the increase in the nuclear pull, because you've added one electron in the 3D suborbital and one proton in the nucleus. So pretty much 1 plus and 1 minus will cancel each other out. And therefore, the nuclear pull on the outermost electrons will be more or less the same.
Sir,
Yes, tell me, Xenia.
can you repeat? Why is the nuclear pull the same?
The effective nuclear pull is the same. So, let's speak about iron. Fe has 26 protons, 26 electrons. Okay? So, if we were to write them with the orbital, so it's 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, 4s2. Okay? So the nucleus is being shielded by these electrons, not blue, and those electrons are 24 electrons. Which means that the effective nuclear pull equals 2 electrons. Sorry, 2 protons. Okay? Not blue. Xenia, taqbel?
Ma kif tapplika l-oħrajn ukoll, jiġifieri kollha ħajkollhom nuclear pull, effective nuclear pull ta' 2 protons.
Pretty much. Pretty much, because
Okay.
you are not adding the electron to the 4s2 or 4p something. You are adding the electron to the 3d subshell. And therefore, the effective nuclear pull will be the same. If the effective nuclear pull is the same, okay, then you are, of course, going to have a similar size. These are about the elements. But of course, if we are going to then speak about the ions, this is all different. Because the ions, you first remove the 4s2 electrons, and then the shielding will be with regard to the second shell. Ma jitkux fihom l-ions hawnhekk. Hawnhekk qed nitkellmu biss fuq the element, fuq the original atoms.
Okay, thank you.
Okay, thank you. Okay, Emily.
Imma kif wasalna eżatt għal 2 protons? Ma tantx wasal iktar.
Kif wasalna għal 2 protons? So if you have 26 protons in the center, in the nucleus, you can see the box, right? Yes.
Yes.
In the center, you have 26 protons. Okay? I'm simplifying the subshells. So these are 24 electrons floating around there. And then you have the last shell that has 2 electrons. So 4s2 here. The first 24 protons will be cancelled out with these electrons. So this area here is all negative, right? It's equivalent to 24 electrons. Therefore, the first 26 protons are going to be neutralized by those 24 electrons. So when the effect goes through the suborbitals, goes through the atom, the last shell is only experiencing 2 protons.
Okay, thank you.
And this number of protons will be the same, this number of effective nuclear pull. Important, the word effective here will be the same for scandium, titanium, vanadium, manganese, iron, cobalt, nickel, and zinc. I skipped chromium and copper on purpose because they're a little bit different. Okay?
Hawnhekk fuq l-għajn qed nitkellmu jew fuq l-element.
Fuq l-element qed nitkellmu.
Alright.
Okay? This has to be about the elements because in reality, the ions, you do not have the 4th shell most of the time. Because most transition elements and the oxidation states is what we're going to be doing next, will actually be at least a minimum of 2+. Copper is an exception where you have Cu+. But normally, you lose both of the 4s2 electrons.
Sir, u wkoll tista' tgħid li fit-T block allura l-ewwel u l-aħħar kolonna mhumiex transition.
Yes, you can, but in reality, you need to know why. So it's useless. It's useless to give you a question and tell me because the first and last columns are not transition.
Le.
Okay?
Alright.
But when I actually, someone asked me a question, whether it's scandium or zinc only, and I actually went to read the elements that are D block but not transition, that's what I've done. I looked at group 1A, I believe, no, group 3B, and group 2B. And I could actually read them from there. Tell me.
Tista' ma dan ir-raġunament ma tista' tgħid li chromium u copper because they don't have an effective nuclear pull of 2 protons, they have an effective nuclear pull of 1 proton, let it.
So they would be a bit smaller.
Chromium or copper. But you still call them transition metals.
Yes, of course. So
even though they don't have an effective.
The definition of a transition metal, this is very important. This is the first thing I wrote on today's board. Okay? The definition of a transition metal is when you have the possibility of having at least 1 ion with a partially filled d orbital. And both chromium and copper can have at least 1 ion with a partially filled d orbital. In fact, chromium can have Cr3+, Cr6+, and Cr7+, which are the common oxidation states of chromium. And all those 3 different elements would be colored. Okay?
Okay, thank you.
Actually, chromium does not have Cr7+, apologies. But all the other oxidation states in chromium, you can find more oxidation states. They are all colored. Anyone want to say something else? No.
So we added to the definition that they have to be colored compounds.
Colored compounds is another property we're going to be speaking about. So up till now we spoke about size, right?
Mhm.
Now I'm going to speak about variable oxidation states. After variable oxidation states, I will speak about catalysis, I will speak about colors, and I will speak about complexes. Complexes and colors are highly related. Okay? But for today, personally, I think once we go and speak about oxidation states, we can stop. Because I think it's enough material for one day, in my personal opinion. Of course, if you want to go and do catalysis, I'm here. I'm going to be here all day long today. Probably tomorrow, I will be here all day long as well. And the day after that, and after that, and then I'm allowed to leave the house. So believe me when I say, the more lessons you want, the more lessons I can give you. Now, are we all clear with respect to size being constant? So size doesn't really change. Are we all clear about this? Okay. A bit more interaction would be really, really helpful, at least for me, huh? Because no one has their screen switched on, which is fine by me. But in reality, I can't assess whether you're there or not. You can be nothing behind the screen, and I will not know.
L-esser, just ħafna tinkwetaw bħalissa għax ħarġu tal-Medtech like report.
We'll speak. Let's finish this.
Statistics, sir.
Very
Sir,
officially,
They are fucking retarded, sir. Imagine, we cannot do any exams in September unless you already applied for them because of as the May session. We're fucked, basically.
Kulla li applikaw f'Mej xorta ħajamluhom u ħajtallawlhom in-numri, so it doesn't make sense. Jew kulħadd jew ħattu.
No.
Wait, listen. Wait a week or two. Because the reality is that, again, just like I had problems in the beginning, the first lesson I gave you online and the second lesson I gave you online, okay, my sound was as crappy as it could be. Okay? It took me time to adjust to find the right program so that I could give you proper lessons. Now, just like I had to improve on what I already had, other people are doing the same thing. Okay? So relax. These things will be sorted. Okay? Now, let's speak about oxidation numbers. Then, if you have any complaints, any worries, feel free to tell them to me and I will try and contact Medtech on my behalf because I have some other students privately who wanted to do things in September. But I would say that if you have these concerns, wait for a week to see what happens. But it's important. Wait. Be patient. Okay? And once you wait for a week, then, and nothing changes, then speak to the school. To the school, I mean the administration. Okay? Now, chromium and copper, strictly speaking, should be slightly bigger. Because the effective nuclear charge will be less. Okay? But again, don't go and look up the numbers. Because the numbers, there are other factors in play here. And
Very or less?
they should be slightly bigger. The effective nuclear pull will be smaller. Okay? But if you go and look up the numbers, there are other factors. Okay? I have the equation. Okay? I have the equation, but I don't want to give it to you because it's something I've done in third year university. And third year university, there were still quite a few students who could not understand it. So I don't want to give it to someone who's doing A-level first year. Mela. Second property I want to speak about is...
Sir, nista' nwaqfek naqa' ħalek naqbes fuq ta' qabel.
Yes, of course.
Ta' chromium u copper. Ħajkunu ikbar għax għandhom iktar electrons fuq ġewwa compared mal-protons. U xek?
Yes, so they will have an effective nuclear pull of 1 because they have an extra electron. They should have 34 right here. They have an extra electron in their d orbital.
Okay.
But don't get confused about chromium and copper because this is a trend that you need to know. And as a trend, don't worry about the exceptions because a trend is a trend. This is like for ionization energy. Do you remember you have a trend? Ionization energy increases along a period. Apart from group 2 and group 3, groups 5 and group 6. And there we actually took some time to explain the differences and to explain the exceptions. Here, we're not doing that because the exceptions are irrelevant. Okay? So oxidation numbers. Oxidation numbers are something that you're probably used to a bit by now. You probably have a good idea that there are variable oxidation numbers. Not blue? So, scandium can be 3+, titanium is either 3+ or 4+, vanadium is 2+, 3+, 4+, 5+, chromium is 3+, 6+, manganese is 2+, 3+, 4+, 6+, 7+, iron is 2+, 3+, cobalt is 2+, 3+, nickel would be 2+ only, copper is 1+, and 2+, and zinc is 2+ only. So these are the most common oxidation numbers, the most common oxidation states of the elements. Now, do you need to know them? No. You will need to know for copper, chromium, manganese, and iron, but even there, we're going to study these in detail. So those elements, we're going to study their compounds in a lot more detail than just speaking about having variable oxidation numbers. Issa. No, Matthew, I just answered that question, okay? No, you don't need to know them by heart. Now, what does it mean that they have variable oxidation numbers? So, if you realize from vanadium onwards, all the elements have the +2 oxidation states, apart from chromium. Okay? And the reason why you have the +2 is because the first electrons that you will lose will be the forest 2 electrons. So the outermost electrons are the forest 2 electrons. Therefore, they will be the electrons that are easiest to lose. Okay? So, because they are the easiest to lose, you will pretty much always have the +2 oxidation state. let's take some note to the ones that do not have the +2 oxidation state. So let's start with scandium. Scandium, if you lose 3 electrons instead of 2, you are going to end up with a full argon electronic configuration. Argon is very stable. Argon is a noble gas, which is highly unreactive. So it's something other elements might want to aspire to be. So argon, scandium then lose 3 electrons to get the argon electronic configuration. Titanium is a bit strange with regards to how we're explaining this. But again, the more electrons you lose, the more difficult it becomes. Titanium is normally, in fact, in the +4 oxidation state. So whilst we have the +3 and +4, titanium is normally in the +4 oxidation state. And in fact, if you were to look at colors of titanium oxide, it is quite dull, okay? Because it is TiO2, it's not really a transition element, and therefore it would be white. Okay? Now, then we start getting the interesting compounds. So let's speak about chromium. Chromium, the outermost electron, has 1. But chromium normally loses 3. Okay, Cr plus is very, very rare. We're going to be speaking about the d orbitals and how they actually divide. So, no, Yannick, the oxides are not normally always white. The oxides, when they are fully oxidized, they could be white. Iron oxide is brown. Chromium oxide, you have the chromate and manganese, for example, they are orange and purple respectively. Now, there is a question too. Why is it that some elements, mainly these, can lose up to 7, whereas the others normally lose up to 3 maximum? So, there's a divide between before manganese and after manganese. So before manganese, you have the d orbital, okay, and you can lose the electrons from the d orbital as well. After manganese, the stable conformation would be the half-full d orbital. So whereas for manganese, you can get 3d5, for example, in Mn2+, for Mn2+, you lose the 4s2 electrons. It will be Ar3d5. Okay? For others, this would be the highest oxidation number. So Fe2+ and Fe3+, for example. Fe2+ is Ar3d6 and Fe3+ is Ar3d5. Today I have already said that having a full d orbital, elements and ions are happy. So if you can get to have a half-full d orbital, the elements and the ions will be very, very happy. Are we clear about that?
Why, sir?
Because being half-full incorporates stability. Okay? Half-full incorporates stability. And because it incorporates...
Chromium and Copper.
Yes, but half-full always does it. Being half-full is always good. Okay? Pretty much, this is something very similar to what we've done between nitrogen and oxygen. Nitrogen has a half-full p orbital, right? When you add the extra electron, there's a little bit of repulsion. And that repulsion you will not want it. Apart from this, being half full is more stable. It's thermodynamically more stable. It's a fact. Okay? Because it's more stable, you will want to try and aspire to be half full. So, Fe2 plus and Fe3 plus. For example, for Fe2 plus, you don't have a half full d orbital. In fact, which is more stable? ion 2 or ion 3? From your experience up till now, which is more stable? ion 2 or ion 3?
Ion 3.
Ion 3. Why ion 3? Because ion 3 has 3d5, so it is half full d orbital. Ion 2 is not. Okay? Now, you might then go on and tell me, what about cobalt? What about nickel? Why don't they go to the 3d5? Because again, it depends on how many electrons you want to lose. Losing 2 electrons here and here, you get to quite a stable conformation. Now, you've never actually done the shapes of the d orbitals, right?
Yes.
I haven't shown you the shape of the d orbitals. We've done up to
Le, konna mill-jom first lesson niftakar, ma JPT konna mill-jom tal-orbiti.
But in reality, they are not in syllabus. Okay? It's because here you have half full d orbital, and here you are going to start pairing up. Now, for next lesson, I want you all to actually look up the shape of the d orbitals. Okay? It's going to be important. And then, next lesson, we're going to speak about the colors and about complexes. When we speak about colors and complexes, these values here will make a lot more sense. But for now, try to understand that you are trying to get to the most stable electronic configuration for the ion. And the most stable electronic configuration for the ion will either be half full, so getting to 3d5, will either be just removing all the electrons and getting to the argon. So here, you lose 7, you get the argon conformation. MnO4 minus, for example, potassium permanganate. Chromium, potassium chromate, or potassium dichromate. Okay? Both are Cr6+. Vanadium, V5+, would be, again, argon conformation. After manganese, it's very difficult to lose 8 electrons, okay, or 9 electrons. So you normally just go to be in the 3d5. When that's not possible, you lose as many electrons as you are allowed. Now, I will be explaining a little bit in the next lesson. How do you know what degenerate means? Orbitals are degenerate. Orbitals have the same energy level. So,
Yes, sir.
I've explained this, and it's in the note as well. But orbitals are, that's fine. Orbitals are degenerate, which means that the d orbitals are all at the same level. So if you were to draw the orbitals, you will draw them like this. Okay? They are all the same. When you have interactions with something that is not in the ion, so for example, with the solvent or with other ions, because the d orbitals don't have the same shape, and this is why I want you to go and look up the shape of the d orbitals, these d orbitals will not remain degenerate. They will not remain at the same energy level, and therefore there will be differences. In fact, 3d7 would become quite stable, for example. But we'll do this next lesson. And we're going to come, again, we're going to make sure that you understand chromium, manganese, iron, and copper as the most important, because those are the 4 elements that you have to study in detail.
Sorry.
Yes?
For copper, why would it prefer losing 2? Like, not prefer, why would it lose 2 electrons? Because 1, it's understandable għax tispiċċa bi 310 to the 10, 3d10 titlef ta' barra, ma 2.
Remember, this is something that I've never actually studied, because this is something probably that is even higher than a master's level. But remember, you are exciting an electron from the 4s to the 3d, right? So if we were to have 3d10 4s0, the energy level the electron would want to be in would not actually be 3d10. It would be more likely to be 3d9 4s1. Again, copper will still probably try to fill that 3d10, but it will probably be more stable and easier to just lose the 2 electrons.
Okay.
Here you are speaking about the energy of a system, the energy of the ion. Okay?
Okay.
Now, Lauren, chromium doesn't lose 1 electron because when chromium loses electrons, both for Cr3 and Cr6+, it actually has a much more stable orbital system. Okay? You are going to see for chromium, we're going to see this when we do the colors, because chromium is the one that we use normally, because chromium is the easiest one to explain. But the d orbitals separate, and you have 3 and 2. But leave it for next lesson. Yes. For most of them, I think it's the highest oxidation number, huh? Emily. Mn7 plus and Mn2 plus, both are very stable. So, potassium permanganate is a good oxidizing agent. Okay, it's a very high oxidizing power. And to get to it is not easy, but it's very stable. When you use it as an oxidizing agent, it reaches the Mn2 plus state. And again, Mn2 plus is also stable. Okay? For these, I was saying, I think these are the ones we're referring to under, right? For those, I said that you can't lose 8 electrons. I don't think there's any compound that has 8 plus or 9 plus. So therefore, they would try to achieve the most stable conformation. And that depends what the most stable conformation is. For example, for iron, it would be 3d5. But you have to do this according to the element, okay? For copper, it's Cu2 plus, for example. We all know that Cu2 plus is more stable than Cu plus and then copper. But then again, copper Cu is also very stable, okay? And Cu2 plus can be reduced to Cu with hydrogen. Now, having said this, the oxidation numbers with respect to what you need to know is that you have variable oxidation numbers, 1, and that these oxidation numbers are a result of the electronic configurations. If you can understand that, for today, I would be very, very happy. Now, I'm going to stop the recording. And I would like